noticed how digital people and analog mixed signal people and software people all seem to come from different tribes? I'm sure in the old days they would have each had their own funny hats and secret handshakes, which today probably just translates into playing on different company softball teams. But what about system verification people? Yeah, we sit here with the systems that have all that stuff, mixed signal, digital, software, and we really don't want to dive into all that inner tribal politics because we might get hurt. It's true. Hi, I'm Amelia Dalton, host of Chalk Talk, coming up with a verification strategy for mixed signal designs, which, let's face it, is almost everything we do these days. Well, it's a long and winding road, with more than a few potholes and construction areas along the way. Today, though, my guest is Steve Carlson from Cadence Design Systems, and he's going to be like our GPS on the road to finding a good verification process that steers us clear of any tribal warfare situations. Before we get started, don't forget to click that link. There you can check out a new book called Mixed Signal Methodology Guide, Advanced Methodology for AMS, IP, and SoC Design, Verification, and Implementation. Hi, Steve. Thanks so much for joining me today.
Thank you, Amelia. Nice to be here with the Internet Superstar.
So I see our subtitle is Long and Winding Road. Now, what road are you talking about, Steve?
I'm talking about the road to mixed signal verification nirvana.
I love it. Okay. Now, mixed signal in the past was kind of a fringe ad hoc collection, right? But it seems like we're going mainstream these days. Steve, what do you think is driving that?
Well, there's some very clear indicators that things have to change. And so it's not because people want to, it's because they're being forced to.
Right.
And I think if you look at some market data from IBS, you'll see that foundationally, there's about 85% of all design starts today are mixed signal in nature.
Wow.
Along with that, you see a lot of cost reduction in integrations going on. So you see analog front end going into these complex digital devices. You see more advanced process nodes, so below 65 nanometers, and so digital compensation calibration is needed.
Yeah.
At 28 nanometer and below, that gets exacerbated with more variation.
Sure.
You have to look at software control algorithms to handle those variation effects. And then, of course, you have to keep up with what your competitors are doing. So as others move forward, you have to also.
Absolutely. It seems like mixed signal is both a technological challenge and an organizational challenge. Is that where we're starting?
Absolutely, Amelia. And if you look at the world that's been sort of a divide and conquer approach to analog and digital design, it's progressed where you see a little bit of digital in the analog and a little bit of analog in the digital. And now it's getting to the point where there's a lot more interaction across those. And so you end up with this idea of a truly mixed signal design.
Right.
And what's interesting, though, is that as these worlds have collided or intertwined, probably better, when a bug appears, what happens is there's a lot of finger pointing that goes on.
Right.
Now, to address the finger pointing,
a
lot of companies have said, okay, what we'll do is we'll hire an intermediary. We'll get that SoC verification team to undertake the task.
There you go.
What that's led to is whenever a bug arises, there's a lot of finger pointing, but it's all at that SoC verification.
Dang it. Okay.
And so they come back and say, well, you didn't give me a proper model, so I couldn't do the verification. And so all the finger pointing goes on. There's just more parties involved now.
Right.
If we look at the interaction between those teams, the division of labor is something that's really important to address organizationally. Who's going to do what?
Right.
What we find, though, is that modeling step still remains a little bit of an orphan and actually requires some collaboration to do a good job of. You have to understand what needs to be modeled to test what aspect of that mixed signal functionality.
Right.
And so this is something that remains sort of an open question, is who's going to do the modeling at what point and for what purpose.
Sure.
Now, as if that wasn't enough, we had our analog and digital. There's a lot of software control in chips today. And so if we look at that software, analog, and digital, that makes us a little sad.
It does.
But there's actually an opportunity here, and it's the opportunity to become a superior ability developer.
Okay, so we're here, and we're sad, Steve. But it looks like we're just in the beginning of this road. Now, where are we going? And gosh darn it, is this going to get better?
It absolutely can, but there's some aspects, some building blocks that you have to put into place. You need some structure, and that can come in the form of verification, planning, and management. You need to have some methodology that's uniform, and there are industry standards out there like UVM, I think you're familiar with.
I am.
And you need to understand that it's going to take more than one underlying engine type in order to execute well on the verification plans.
Sure.
And of course, there's different modeling languages that are associated with those different engines. And then those languages have aspects to them such as constraints and continuous time versus discrete time, et cetera. And so you end up with a big ABC soup of new acronyms that you're going to have to use.
It looks like it. Now, that's a lot of change. As we go down this road, what do we expect to gain once we get there?
Well, there's a lot to gain, and I think the uniformity that you get from applying the structure, you get some productivity from the reusability and the application of standards, and that reusability is people as well as the artifacts that they've created as well.
Sure.
The management can quantify progress, and you can say where we are in the process. You can be more efficient by using a multi-engine approach rather than trying to build your whole house with just one hammer.
Right.
You need some saws and nails and other things as well. And then, of course, using a language that's efficient to express what it is that you're trying to do.
Okay, I'm starting to think we might need that GPS lady. Gonna need some directions to improved mixed signal verification here.
Well, luckily I have a map.
Okay.
So as we start with this vexing problem of mixed signal verification, the first step is to look at co-simulation, and this is where you combine the analog and the digital solvers together. When you try to run any amount of digital circuitry in an analog solver, it's extremely slow and quickly overwhelms the engine.
Yeah.
The real key to moving forward is to address the modeling issue, to get an abstraction of the analog behavior so that you can execute orders of magnitude more fast.
Okay.
Then starting to add metrics into the equation and measure the effectiveness of your tests. The next step is often people are looking at modeling the power management features that are put onto the chips, and this includes, overlays like power shutoff and multi-supply voltages, sometimes variable supply voltages. That can be then transformed into a planning and management discipline, where you're organizing your tests by type and feature.
Sure.
And then this idea of applying UVM is important as well, and that gives you those industry standard practices. From there, we want to go still faster because we want to start looking at that software aspect to it, and that requires still more performance. And so we look at adding hardware acceleration and being able to go into a software-driven test bench discipline.
Okay.
And from there, you're pretty much at fame and fortune in terms of mixed signal verification.
Excellent. You got me there. Okay, so Steve, one of the common complaints that I hear about mixed signal verification is that it's slow. What about that?
If you try to do everything in a SPICE engine, then, absolutely you're very limited in terms of the scope that you can work, the number of transistors and the number of waveforms that you can put through. There are ways to do some abstraction that gets you through the fast SPICE kinds of engines, and so we'll talk a little bit more about that. But the real big jump is when you change the modeling abstraction from transistors into a discrete time, real number modeling approach. And you can go even faster and get onto specialized hardware if you model everything as if it were logic.
Okay.
But that's not applicable to every kind of test, the purpose of every test. Some require a great deal of detail, some require minimal detail.
Okay, so I can see that I can trade off speed for accuracy, but how exactly do I do that?
Well, let's start with the engines first. So one thing you can do is improve the speed of your SPICE engine, right?
Okay,
and so at Cadence, we actually have a couple different steps that you can take beyond the basic SPICE engine of Spectre and go to Spectre APS, which is the Advanced Parallel Simulator, a multi-core solution.
Okay.
And then we have XPS, which is an accelerated version of that. The next step would be to start mixing analog and digital solvers together. And so you bring the incisive digital solver working in conjunction with the analog solver of XPS.
Okay.
To move still faster, then we convert the analog netlist into a real number model representation and combine it with the incisive engine, and that lets us simulate the analog and the digital together in the same discrete time engine.
Okay.
The next step from there would be to put the digital part of the chip onto specialized hardware. So we have emulation acceleration technology here, and that can talk to the workstation host to the real number models. Now there's also what I put a fifth step here that's very specialized and specific in nature. A couple of our customers have done where you have the fast spice engine talking to the hardware and the host. Sort of an exception case, but it's something to look at if you have very small analog talking to a very complex digital system.
Okay. Now, I have been using Spice, but what if I want to go really fast?
Well, if you still need that accuracy of the analog solver, then the XPS mixed signal mode has recently been introduced, and what we're seeing is from 3 to about 10x speed up with just changing engine. So you can get a dramatic boost from that first step.
Absolutely.
Now, beyond that, I have a little table here that shows the relative speeds of these different configurations of engines and models that you can use. And so starting with a normalized basic SPICE engine, Spectre, being normalized to 1, and then we can go to XPS, running about 10 times faster. And then when you mix the XPS and Incisive together, you can run about 100 times faster. And then when you do real number modeling of the analog, then we're talking about 1,000, 10,000, sometimes even more than that kind of speed up.
Oh my goodness. Okay, so it seems like I have a lot of problems to tackle, but how do I figure out what to take care of first?
That's a really good question, and it varies depending upon what your starting point, what the expertise is in the organization. But certainly the first step is to make sure that you are using multi-domain simulation. So you're using the efficient engine for what it is you're trying to model. Often companies today are being driven to change in methodology by the incorporation of complex power features that are controlled digitally. This is a trigger point for methodology change in many organizations, and that is usually accompanied by the switch to the use of real number models that really facilitate that speed up that you need in order to get the execution time for the coverage of the different features and functions of power management.
Okay.
The next step is being able to effectively measure what it is that you're testing, right? And so coverage metrics come into play. And then again, the whole discipline of UVM, and again, going to the hardware acceleration path at the end to really be able to bring in the software.
Gotcha. Okay. So my team has analog people and digital people, and they're used to working in totally different ways. Now, Steve, how do I get them on the same page?
We don't know if that's possible or not. And so we took a little different approach, and we actually provide the same engine technologies in 2 different ways. And one is having sort of the analog-centric graphical environment, and the other is the more language and script-based regression environment for the digital folks. So that lets them use the same engine technologies and share data across the environments so they have the same answer, but in a form that they best understand.
Right. Now that everyone is mostly on the same page, and it's still not fast enough, where do we go from here?
That first step is the big step, and that's getting to that real number modeling. And this is where we take analog behavior that's been described in a continuous time manner in SPICE models, right, codified into SPICE models, and convert that into these discrete time real number models, where we can use a digital solver. And this is a hurdle in many organizations because the expertise on the behavior of the analog lies in the analog domain, but language-based design is really that of the digital domain.
Right.
And so the two need to meet, and that's often the hurdle that we need to overcome. There's a lot of industry standard support around facilitating that, but you still have the human element that needs to be overcome.
Right. So how much faster can we go with real number modeling?
Well, I have a small example here that's easy to understand. We have a back-to-back analog to digital, digital analog converter.
Okay.
Texas Instruments did a little study where a 14-bit converter, it took them several days in the analog solver to go through all the steps of conversion. In a real number model, it's 3 seconds.
Wow.
So you can see there's quite a bit of productivity to be had if you do take this modeling step.
And then some, yes.
But to take this step, we have to get that language-based model.
Right.
And so System Verilog, the language reference manual, has undergone some changes in order to facilitate the use of analog behavior models within the digital verification environment.
Okay.
And so there are some things called bus resolution functions and other constructs within the language that let you plug together analog behavior and digital into one environment and apply that digital solver that runs so fast.
Mm-hmm. That sounds great, Steve, for my digital guys, but what about the analog folks?
That's a tough one because they don't want to use language, right?
No, they don't.
And they're much
they
more
like
comfortable.
Pictures, right?
Absolutely, they like pictures. And so we have something we call SMG, or the Schematic Model Generator.
Okay.
And that starts from within the Virtuoso environment. So they have their transistor level schematic up. And what they can do is create a model from a set of building blocks that we provide, and they're parameterizable, so they can drop down these building blocks, connect them together schematically, and then generate the real number model from that can then go into a simulation environment. And so without having to go to language-based design, they get the simulation accelerated benefits of it.
Excellent. So in addition to our base functionality being verified, we also have all of this power management mechanism running through just about everything we do. Now, how do we handle that?
That's a real driver for change in verification technologies, because it's actually a new dimension to an already multi-dimensional problem.
Right.
And so we just explode the number of tests that are needed, and you can't possibly run as many tests that are required in SPICE to verify all this new capabilities that's being put in.
Right.
So we have, on top of the languages I've already talked about, there's the idea of a power intent specification, or a power intent file. And there's a couple of standards. We have the common power format from SI2 and the unified power format from IEEE.
Yeah.
Then we support both of those. The example that I'm showing has CPF, but we equally support UPF. And as we're modeling in real number models, we still need to do the power aware signal conversion.
Okay.
We need to model the power supply information. In the digital world, we don't have to worry about that. But when we're talking about analog behavior, we have to do that. And we have to look at dynamic violations on the mixed signal boundaries. Now, this behavior often includes states and modes that are described within the power intent file. So this is that added dimension is sequential in nature. And that means that there's a lot of time associated with that. And so the modeling of power switches needs to be incorporated, as well as the management of the modes, which have a functional implication potentially for each change in power mode and voltage value. The constructs of the languages allow you to use real numbers. So that's already been provisioned for. So the CPF, UPF infrastructure that's there luckily anticipated the necessity of incorporating mixed signal behavior into the solution. So we can do that right now.
Okay, so with all this ad hoc we've been using, it's really difficult to tell how much verification we've done. So what you have and have not verified?
You're right, Amelia. The testing methodology that we find in sort of the legacy, or I'll call it traditional approaches, is very much a single test bench. And as you find new features to test, you just add it on to the end of the waveforms and keep testing more and more in a single test. Kind of the first step is to break that up into smaller tests, right? And we're going to be headed towards sort of a regression approach where we run a whole bunch of small tests rather than one big, long one. We can get some productivity doing that. The next step is to create coverage metrics for those tests. And so we understand what we've tested and what we have not. And have not is pretty important.
Right.
And from there, we can actually go to a more disciplined approach where we categorize and plan ahead for what we're going to test and how we're going to test it, and then measure against that plan. And so it kind of builds this pyramid of capabilities up.
All right, Steve. So does this have anything to do with UVM?
Yes, Amelia, it has everything to do with UVM. And the structure and reuse, the standard nature of UVM is a great asset to making the switch to this methodology pay off. And it lets you reuse across people, as well as, again, the artifacts that we talked about, all the test bench and infrastructure that you build.
Yeah.
And so just diving in a little more, when we talk about a UVC, a universal verification component, it actually provides a discipline, a specific structure to the way we're going to create the test bench around the design that we want to test. And it incorporates the generation, checking and coverage elements of the test together. Little example of what that diagrammatically looks like. It's a object-oriented approach to test. And so there's a test environment that gets put together and then adapters that let you attach to the design in a configurable manner. The real number modeling aspects are available in the environment and the sequencers and agents, etc., as well as at the port of the design. So as we want to customize for a particular design, we can do that, and we can use real valued signals, floating point valued signals, to attach to the device under test.
Okay. So we've been doing just fine helping out my analog and digital folks, but what about my software guys waiting in the wings?
The software guys are there looking over everybody's shoulders these days. They need to get
Always.
started sooner, right?
Yep.
Everything's got to be sooner. And so it becomes really important to be able to run these simulations fast enough to move to a software-driven test bench sort of solution so that you can test the algorithms for calibration and compensation, or the functional behaviors, the actual applications as well.
Right.
So here I have an example. A company called Medtronic gave a paper where they were able to get all of the design onto the hardware.
Okay.
And what that enabled them to do was to run their C++ test benches directly on the device, and they were actually able to run faster than at speed.
Really? Faster?
Faster than at speed. So quite incredible capability. Special case of lower frequency medical devices, but nonetheless very impressive.
Very impressive. All right. So, Steve, we've been on this road trip for a while now. Are we there yet?
We have arrived.
Okay.
But there's one more stop along the way.
Uh-oh. Okay.
At least. And where we'd like to go next is to take this up into the system level, and
Sure.
so that we can do a better job in earlier system design and performance modeling, including the analog behaviors of the design and the limitations there, looking at the power, thermal envelopes, things like that, as well as driving that abstraction across and be able to do multi-abstraction design so that we can get still greater performance improvements.
Okay. Now, this has been a lot to take in today. Let's walk through your main points one more time.
All right. So the basic challenge is that divide and conquer analog and digital doesn't work very well anymore. And so as those come together, we see that the simulation speed is a primary hindrance in being able to comprehensively address the verification problem. Our approach is to use sort of the best practices from the digital realm and apply them across the mixed signal domain, across both the digital and the analog, and incorporating software as well. And so there's things like planning and management, UVM, using real number models, the metrics, using a multi-engine approach, so the analog solver for its purposes, the digital for its, and specialized hardware when we need it. Along with that goes the modeling at the proper level of abstraction. And then there's a few languages, and we provide a full host of choices depending upon what it is the customer is trying to achieve. The solution that we provide is comprehensive of all those aspects that we talked about. So a full range of configuration of engines, giving you access to the most efficient engine for the particular verification job that's using in the context of this metrics-driven UVM mixed signal verification technology. As you saw, that's a lot to cover, and there's a lot of resources that we provide. And there's two good books that are starting points, one having to do with digital-centric UVM practices, and the other having to do with mixed signal design, covering both the verification and design implementation aspects. We have a number of customers that have also done papers about their experiences. So we reference here ST Ericsson, ST Proper, as well as really interesting work by Freescale, Arthur Freitas and company. And we have workshops and white papers and all kinds of resources associated with that. When we look at all that finger pointing that we talked about in the beginning, there is a cure for that, and it is this mixed signal verification methodology with UVM, and we can get from finger pointing to more of a divine finger touch.
I love it. Well, Steve, I think that's all I have time for today. Thank you so much for joining me.
Thanks a lot for the opportunity, Amelia.
Before we go, don't forget to click that link. There you can check out a new book called Mixed Signal Methodology Guide, Advanced Methodology for AMS IP SoC Design, Verification, and Implementation. For Chalk Talks, I'm Amelia Dalton. For more Chalk Talks, check out the EE Journal YouTube channel or the on-demand section of eejournal.com.